In this video, we will calculate the information entropy. In information theory, we can calculate entropy using this equation: the logarithm of W with base 2. W is the number of possible outcomes with equal probability. So if we flip a coin, there are two possible outcomes: heads or tails, 50-50 chance. Therefore, the entropy is 1. The logarithm of 2 is simply 1. If we roll a die, there are 6 possible outcomes with equal probability, and then entropy is the logarithm of 6 with base 2, and this is 2.6. With more possible outcomes, we have a higher entropy. We can also calculate the entropy of numbers. Let's look at this number. The entropy of this number is 0 because the value of this binary number is certain. There's no uncertainty. Also, we can tell the value of this W for this number is just 1 because this number has only one possible value. Now let's look at a different number with 2 question marks. In this case, this number may take one of 4 different values. Therefore, the entropy is the logarithm of 4. The result is 2. Or we can look at this number and we see 2 bits are uncertain. Therefore, its entropy is 2. 2 quiz questions. Calculate the information entropy for this binary number and this decimal number. First, let's look at this binary number. 3 bits are uncertain. Therefore, the entropy is 3. Also, when 3 bits are uncertain, we have 8 possible values. So we can take the logarithm of 8. We get 3. Over here in this decimal number, we have one uncertain digit. This question mark can be 0, 1, 2, all the way to 9. There are 10 possible values. Therefore, the entropy of this number is the logarithm of 10, which is 3.3. The entropy of this decimal number is higher than the entropy of this binary number. But what if the outcomes have unequal probabilities? When that's the case, we have a slightly more complicated equation. So we're looking at all possible outcomes and assign a probability to each outcome. And then we use this equation. We have logarithm of the probability multiplied by the probability. And we sum over all possible outcomes and then put a negative sign in the front. We get the entropy. Now here's an example. When we flip a rigged coin with 90% chance of getting heads and 10% chance of getting tails, and then we can calculate the entropy using this more general equation. So this P stands for probability. And we have P sub 1 and P sub 2, 90% and 10%. We plug in the numbers, 90% here, 90% here, 10% here, 10% here. We do the math, we get 0.47. So for this rigged coin, the entropy is 0.47. With a fair coin, the entropy is 1. So when we rig a coin, we lower the entropy of the coin toss. Again, entropy is a measure of uncertainty. Therefore, when we rig a coin and increase the chance of getting heads to 90%, we know more about the result or the outcome of the coin toss. Therefore, the entropy decreases. So mathematically, we can calculate the entropy for all different probability distribution. The probability of heads can be from 0 to 1. When it's 1/2, the coin is fair. The entropy is maximized. And if you calculate this, the result is simply 1 over here. If we have 100% chance of getting heads, the entropy is 0 because the outcome is certain. What if we have 100 probability of getting tails? Again, the outcome is certain, the entropy is 0. Entropy is a measure of uncertainty. Here we have an academic example. If we change the grading option from A, B, C, D, F to pass or fail, the entropy decreases. Now let's do some numerical example. Assuming 20% chance of getting A or B or C or D or F, we can calculate the entropy using this expression. It's -5 times the probability times the logarithm of the probability. Only because this p sub I is the same, we can simplify the expression this way. The result is 2.3. But what if we change this option to pass or fail? Again, A, B, C, and D are pass. F is fail. Now we have 80% chance of passing and 20% chance of failing the class. Now plug in the two numbers, 0.8 and 0.2, the entropy is only 0.7. So when we have a wider grade distribution, we have 5 categories here, higher entropy. When we have only 2 categories, pass versus fail, we have narrower grade distribution. Entropy is 0.7. In thermodynamics, we do similar calculations, except one change. We use energy levels to replace the grades.